Welcome to another video, and for today we'll discuss continuity. On the previous lessons that we had, we already have discussed that the limit of f of x as x approaches c is not always equal to the f of c. Now, this idea leads us to the study of continuity of a function. Now, we can say that a graph of a function is continuous if there are no holes, breaks, or asymptotes that can be found on that graph of the function. What I meant when I said that the graph is continuous is if you are able to draw the graph of the function without lifting your pen, then the graph is continuous. Say, for example, we have here the Cartesian plane, and then you have the graph of a linear function. If you're able to draw the graph of this function without lifting your pen, the graph is continuous. Another example is if you have a graph that looks like this, or a graph that looks like this. Now, since you were able to draw the graph of these functions without lifting your pen, then you can say that a graph of these function is continuous. Now, how do we know that a graph of a function is continuous? We have here a continuity test. A function f of x is continuous at x equals c if it satisfies these three conditions given. First, if f of c exists. Second, if the limit of f of x as x approaches c exists. And last is if the limit of f of x as x approaches c is equal to f of c. Now, if one or more of these conditions are not satisfied, then the function is said to be discontinuous at C. So this is continuity at a point. Now let's have an example on how to identify if a graph of a function is continuous at a point. Say for example, we have the function x to the fourth minus 2x squared plus 3x minus 5, and you are asked if this function is continuous at x equals 1. Now, how do we solve this one, or how do we identify if this function is continuous at x equals 1? Now, we will be using the three conditions that we have previously discussed. So the first condition is if f of c exists. Now, our value of c here is 1. So let's evaluate f of 1. So this becomes 1 to the fourth minus 2 times 1 squared plus 3 times 1 minus 5. This is 1 to the fourth is 1 minus 2 times 1 is 2 plus 3 minus 5. Now, simplifying this, we get negative 1 plus 3 is positive 2 minus 5 is negative 3. So we already have our first condition. Now, the second condition is if the limit of f of x as x approaches c exists. Now, we will be solving for the limit of x to the fourth minus 2x squared plus 3x minus 5 as x approaches 1. So by substitution, we have 1 squared minus 2 times 1 squared plus 3 times 1 minus 5. This is 1 minus 2 plus 3 minus 5. 1 minus 2 is negative 1 plus 3 is positive 2 minus 5 is negative 3. Now both our first and second condition exist. So let's now move on to our third condition. That is, if your f of c is equal to the limit of your f of x as x approaches c. Now, the value of our f of c is negative 3. Then the value of our limit of f of x as x approaches c is also negative 3. Therefore, this graph satisfies our third condition. Now, What we have discussed earlier is the graph of the function is continuous if it satisfies the three conditions given. Now, it satisfies that f of c exists, the limit of f of x as x approaches c exists, and since their values are equal, then it satisfies also the third condition. Now, it satisfied the three given conditions. Therefore, this function f of x equals x to the fourth minus 2x squared plus 3x minus 5 is continuous at x equals 1. Now let's have another example. Say we have a piecewise function f of x equals x plus 1 if x is less than 3 and x minus 2 squared plus 1 if x is greater than or equal to 3 at x equals 3. Now we'll be identifying if this function or this piecewise function is continuous at x equals 3. Now let's solve for the first condition, which is the f of c. F of 3 is equal to what? Now, we will be deciding which function will we use in solving for f of 3. Now, in the conditions given, if x is greater than or equal to 3, you will use this function. Therefore, we will make use of the second function. This becomes 3 minus 2 squared plus 1. Now, simplifying this one, this is 3 minus 2, which is 1. 1 squared is 1. Plus 1 equals 2. So it satisfies our first condition that f of 3 or f of c exists, since this is not undefined, so it exists. Now let's solve for the second condition. Second condition says that the limit of f of x as x approaches c exists. Now let's try to solve for the limit of this function as x approaches c. Since this is a piecewise function, it's better that we solve this one by looking at the one-sided limits of this function. So let's solve first the limit of f of x as x approaches 3 negative, or values less than 3. Now, the condition says that if x is less than 3, we will make use of this function. So we will use x plus 1, so substitute 3 to x and then plus 1. Therefore, the limit of f of x as x approaches 3 negative is 4. Now let's try to solve for the limit of f of x as x approaches 3 positive, or values from the right of 3. Now values from the right of 3 are of course greater than 3, so we will make use of this second function. So if we substitute 3 to the function, this will become 3 minus 2 squared plus 1, and we know that 3 minus 2 is 1 squared is 1 plus 1 is 2. Now, the limit of f of x as x approaches 3 positive is 2. Limit exists if and only if the one-sided limits are equal. Now, since your one-sided limits are not equal, therefore the limit of f of x as x approaches 3 does not exist. Now, it does not satisfy the second condition. Now, as what we have discussed earlier, if one or more conditions are not satisfied, then the function is not continuous at a point. Therefore, the function f of x equals x plus 1 if x is less than 3, and x minus 2 squared plus 1 if x is greater than or equal to 3 is not continuous at x equals 3. Now we also have this continuity on an interval. Now what is continuity on an interval? The same with the concept of continuity at a point, you can say that a graph is continuous at every point on an interval if you are able to draw the graph of the function without lifting your pen or without being interrupted by discontinuities like a hole or a break or asymptotes. Now, before we move to our examples, let us have first these known facts about continuities of functions on intervals. First is that polynomial functions are continuous everywhere. Second, absolute value functions are continuous everywhere. Third, rational functions are continuous at every point or every number in its domain. And fourth is if your function is a radical function, if n is a positive integer in that your function is equal to the nth root of x, then if n is odd, the function is continuous at every number, and if n is even, the function is continuous at every positive number. Now, these are the known facts about continuities of functions on intervals. Now we will now move on to our examples and apply these known facts about continuity on intervals. Let's move to our first example. Determine the largest interval over which f of x equals the square root of x minus 4 is continuous. Now notice that the index of our radical function is even since the index is 2. So it's even, meaning the function is continuous at positive numbers only. This means that the radicand should be greater than or equal to 0. So we write our radicand x minus 4 greater than or equal to 0. Therefore, our x should be greater than or equal to positive 4. Now remember that since we cannot make a radicand negative, the function is only continuous for values greater than or equal to positive 4. Thus, the largest interval over which this function is continuous is x is an element of an interval half open on the right from positive 4 to positive infinity. This is our final answer. Now let's have another example. We have f of x equals x plus 2 all over x squared minus 1. Now remember that the domain of this function is the set of all real numbers except for values that can make our denominator equal to 0. So let us try to look what are the values that can make our denominator be equal to 0. So let's focus on our denominator. So we have x squared minus 1. And we know that this is factorable, so we factor this out. This becomes x plus 1, x minus 1. This is just the difference of two squares. Now let us equate our two factors to 0. So we have x plus 1 equals 0 and x minus 1 equals 0. So we get x equals negative 1 and x equals positive 1. Now, since negative 1 and positive 1 can make our denominator equal to 0, therefore our final answer is that x is an element of real number such that x is not equal to plus minus 1. So that ends our discussion about continuity. And in the next lesson, we will discuss discontinuities. So that's all for this video, and thank you for watching.